Hello Chemistry. This is a video for section 2 of chapter 15 on page 491, and I'm going to try to do some illustrations here to illustrate the concepts that are coming from this section. A little bit hard for us sometimes to grasp to start with, but once it clicks, it's not so bad. So here I want to start with an illustration to try to explain what we're going to do. You see, we often don't know what's in a chemical. We can't see it. We shouldn't be able to taste it or anything like that. So how do we know how concentrated it is, how much it's in there? Because we need to know. Well, we're going to use this analogy here to get the concept going. First of all, let's say that I have a balance and I put some weight on there. How could I find out how much weight that is if I don't know how much this is? Well, I could put other weights on here until it tips the other way. And now I've got too much. So how could I figure out how much that is? Well, I could take this one off and I could put a smaller one on there. And if it balances, then I know that this must equal that. In this case, it's 200 plus 200 plus 100. Oh, this must be 500 grams. Well, what if I don't know what it is? So this is going to be our chemical that we don't know, and I'm going to put a mass on here, and I need to figure out how much is there. Again, we're going to use the same kind of a thing. I'm going to put these masses on there, and I'm going to put a bunch just to start with to see how much it is. Well, that went too far. So I'm going to take some off, and I'm going to put some smaller ones on there. And take it a few at a time until I get closer and closer. Until it balances. Once it balances, I can add this up and I know how much the mass on the other side is. Now, one of the nice things about this scale is I can take off or add if I want to. But in chemistry, when we're mixing chemicals, I can't take chemicals back out of the container. So once I put one on this side, I am committed. So let me illustrate how that would work. Let's say that I have my unknown on this side. What I'll have to do is I can't take all day. So I tend to start out going a little bit fast, and I might even put something like oh, that didn't go. I might put something like this in it. Oh, I went too far. But I can't take it off. So what I'm going to have to do is I'm going to add some chemical on this side to get it to where it balances again. So I'm going to be a little more careful. I'm going to add 50 to this side. I'm going to add another 50, and we get to be balancing. Now in titration, it's a little bit hard to tell because we're going to use an indicator to tell. So I might add just a little bit more to be sure to change color, and then I'm going to add back to this side until we get to balancing. Once we're balanced, then I know however much is on this side must be how much is on that side. And that's the concept we're going to use to figure out our concentration of our solution that we don't know what it is. So what we're going to use is this apparatus. And we're going to put our unknown chemical into one burette and our known chemical into the other burette. And we're going to start by putting some of the unknown, actually it doesn't matter which one, we're going to put it into this flask. This flask is called an Erlenmeyer flask. Now, to be able to tell what's happening, the thing that's going to show us when we're at equilibrium, just like the scale here showed us when we were at equilibrium, is going to be what's called an indicator. The indicators we've already talked about, in your book, you have a discussion of indicators. We did the red cabbage lab, and we used the litmus paper as indicators to tell us when something is an acid or a base. The one we used was red cabbage. The one we're going to use for the titration when we do the lab is called phenolphthalein. So we're going to put in here our unknown, and we're going to put in an indicator that's going to change color. Now, one of the tricks is, when does it change color? Not all indicators change color at the same pH. So your book has a whole bunch of indicators here, and at what range they change color. So the one we're going to use here is phenolphthalein, and it says it's clear if it's below 7, and it starts to turn pink when it's above 7. And that's the pH numbers that are here. If you go up to these, and by the way, you'll see little black marks showing you the range at which it's going to change color. Now, up here on these different ones, methyl orange and bromethyl blue and so forth, they change way over here at 7. So there may be times when we don't want to know when a solution is neutral. We want to know what's the pH, either acidic side or basic side. And so we have the different indicators that work well to tell us the different things. Turns out some of those are kind of poisonous, so some of them we don't even use in high school because of the safety concerns. But phenolphthalein is safe, and that's why we're going to use it for our lab. It also tells us when the pH is 7, and it's a fun one to do. So when we go to doing our balancing act, we want to get to the point where we can change the color of our indicator by just one drop. So that if we add just the smallest of masses, I can add the smallest one to the other side, and I know that it still balances. Then I've reached that interval. Because, as it points out in your book, there's a graph here on page 497. It turns out that we can add a lot of mass to one side and not get much of a change for a while. And then all of a sudden, it takes just the tiniest of amounts. We could put just the tiniest amount on this. This is 1 gram. I could put that tiny bit, and it tips it that side. And if I put 2 grams on this side, it changes it completely the other way. So even a very, very small amount, 1 drop, will make a dramatic change. And that's why, to get it exactly balanced at 7 for a pH, we have to have just a small amount. The big amounts will not be as important. So we have to watch our transition interval, because just 1 drop will shoot us a huge difference in pH. So let's talk about some of the vocabulary in this section. First, the thing that changes color on page 491 that tells us what the pH might be is an indicator. And we put that here in the Erlenmeyer flask. On page 492, transitional interval. That is the range at which the indicator will change color. So for the phenolphthalein, which is what we're going to use for our lab, that changes over around 7. But other indicators change at other ranges, and that's the transition interval. We'll come back to page 492 at the bottom, but on page 496 there's another vocab word, and that is equivalence point. There's equivalence point and end point. So equivalence point is the point at which 2 solutions used in a titration are present in chemically equivalent amounts. So when this is balanced, we have reached the equivalence point. There's another word that gets a little bit confusing, and that's in the same paragraph. It says the end point. The point in a titration at which the indicator changes color is called the end point. For our lab, our equivalence point, we want to find it when it's pH of 7. So we have just as much of acid as we have base, and it's balanced. That's what we want to find the equivalence point. So we need to find an indicator that has an end point that is also at 7. In this case, phenolphthalein is why we are choosing this. you see for these other indicators, their endpoint is different. Like here, the endpoint would be at 5. Here, the endpoint is over at 3 or 4. And so not all indicators have the same endpoint as equivalence points. And so you need to understand the difference between those two concepts. Now, I'm going to come back to page 492, and we talk about, by the way, there is the vocab word. It's not underlined or bolded or highlighted. Universal indicator, right there. And we did the pH paper that has all the colors. Cabbage juice is a universal indicator. Litmus and phenolphthalein are not universal indicators because they either change one color or the other at a certain point. Whereas universal indicators change over a whole rainbow of colors. And right below it is what's called a pH meter. A pH meter is a digital device that is used to calculate or find the pH of a solution. pH meter determines the pH of a solution by measuring the voltage. This is something I want you to know. Measuring the voltage between two electrodes that are placed in solution. So you remember that a acid or a base is a conductor of electricity. It's an electrolyte. And so by putting two electrodes into the solution, it can measure how much electricity is going between the two electrodes. And the more electricity goes, the higher or lower the pH must be. And so that's how a digital pH meter works. But the indicators were used long before there were pH meters. Now, the process we're going to talk about next comes on page 495, and it's called a titration. So we're going to push this guy out of the way, and this is our apparatus for the titration. We will put into one burette an unknown concentration and the other burette a known concentration. So we're going to compare the two to try to figure out what our unknown is. And you will not be able to see what's in the fluids unless we put an indicator into our container. We're going to use phenolphthalein, and we'll start by putting some in here. And it really doesn't matter how much. We just put some. It's just like it doesn't matter how much gets put on the scale. We just have to put something. And then we're going to put some of this one in here until the indicator changes color. When the indicator changes color, then we know we've reached our endpoint of our indicator, which also happens to be, for phenolphthalein, the equivalence point. We're going to use a standard solution, which is a vocab word on page 497, to use to calculate our unknown solution. So on page 498 and 499, it talks about the process. First, we're going to fill up our burettes up here to 0. Now, right now, I have them above my eyes, but we usually try to avoid having our burettes above us. Why do we want to avoid that? Because we don't want to have any spills of acids from above us down onto our face and our eyes. We fill them up to here, and then we will let some of the solution into the Erlenmeyer flask. We will let some of that into the Erlenmeyer flask, and we will measure its volume. Then we'll put, we actually won't record it yet. We're going to put some of this in here, and when we reach our equivalence point, we're going to write down how much of each one went into the solution. We're going to use the concentration of the one we know. We're going to use the chemical balanced reaction to figure out the mole ratio, and then from that we'll calculate the concentration, which I will show you in just a moment. So let's take a look at the example in your book about how to do the calculation for a titration. This is on page 500, and they give you the example of supposing you had 20 milliliters of sodium hydroxide and you know the concentration. And it found the endpoint at 10 milliliters, but we don't know the concentration of the hydrochloric acid. So how can we find the concentration of the hydrochloric acid? Well, first of all, we have to have a balanced chemical equation, which is easy to forget because a lot of times it's a 1-to-1 ratio. So it is a temptation to get a little sloppy at it because in this case it's all ones. So the math ends up not really mattering too much, but we have to watch out. If it's ever a 1-to-2 ratio or 1-to-3 ratio, it could be different. But our sodium hydroxide is our known, our hydrochloric acid is our unknown. So first of all, we need to know how many pieces, how many hydroxide ions did we use to get this. Then we'll know how many pieces. If we know how many pieces of this, we're going to have the same number of pieces of this. If we have the number of pieces, we can compare that to the volume, and we can know the concentration, because concentration is the moles per liter. That's what molality means. So how do we find out how many pieces or moles of sodium hydroxide we used? Well, it told us that it's 5 times 10 negative 3 molarity. So that means that's the same as saying moles per liter. Molarity is moles per liter. So there they have it. So it's really kind of a conversion factor. Oftentimes we would have started with the 20 milliliters on this side. And you'd write your 20 milliliters and then times our conversion factors. So I want to write it out a little bit more the way we might more commonly do that, and that's to put the 20, our given information, to start with. And then we're going to use our conversion factors. So our conversion factors are molarity, and we know that for every, and we're going to have to convert milliliters to liters. So that's why they have here the 1,000 milliliters to 1 liter. That's a conversion factor. And then we have to use the molarity, which is for every 1 liter, we get 5.00 times 10 to the negative 3 moles of sodium hydroxide. And these are our conversion factors, and this will tell us then how many moles of sodium hydroxide were used. So it turns out to be 1 times 10 to the negative 4 moles of sodium hydroxide was used. Well, if we used 1 times 10 to the negative 4 moles of sodium hydroxide, well then how many moles of hydrochloric acid did we use? Since it's a 1-to-1 ratio, it'll be the same. So here we take our results from here and we put it back into a calculation. So I'm going to do the same thing. 1 times 10 to the negative 4 moles of NaOH. So that's our given. Our conversion factor is our mole ratio. So we have 1 mole of HCl to 1 mole of NaOH. And like I said, this math is so easy because it's a 1-to-1 ratio. We get the exact same number. Ta-da! But it's a different substance. It was moles of HCl. It's a 1-to-1 ratio. The numbers are the same, but we had to do the mole ratio. Now, so what's the concentration? If we have this many moles, how do I find the concentration of the hydrochloric acid? Well, they told us that it took 10 milliliters. So I know I have this many moles in 10 milliliters. The catch is I have to then take this divided by milliliters, but molarity is always in moles per liter, so we have to do one more conversion. We have to convert milliliters to liters, and then we get our concentration. So I could have been a little bit lazy, and I could go 1.00 times 10 to the negative 4 moles HCl, and divide it by, instead of saying, do this conversion, I can just move the decimal over 3 places, 1, 2, 3, and I get 0.01 liters. So I get moles per liter, but this is not a 1, so I'm going to have to do a little bit of math. And since these both happen to be 1, my exponent just changes, as you can see, to 1.00 times 10 to the negative 2 molarity of HCl. And that's our concentration of our unknown solution. So, quick review. We take our volume of our known and do the conversion to find out how many moles of it we used based on its concentration. So this is the molarity. And then we use the mole ratio. to find how many moles of the other unknown we used. Once we know the number of moles, we divide it by the volume, and ta-da, we know what the concentration of the other substance was.